It was that much better. So, second property will have a clustering effect. It's the idea that friends of my friends are also my friends. And third, as we've been hearing quite frequently over today and yesterday, I'll have a power law degree sequence. Roughly speaking, it's a relatively sparse graph, but there's some still some high degree vertices. And many of you can fill in quite a few more examples of these, but here are a few. So things like website links on the internet, citation graphs, package dependencies in the Java programming language, and some semantic networks in English. Certainly you guys can add on many more than these. What I want to highlight with this is that many of these examples I've just presented here, they don't have an obvious geometry that you can put underneath this. That's going to come up in a second because, well, there's been a lot of work by those of you in the room and elsewhere to model these things via random graphs. In particular, some of the first few models, of course, preferential attachment, Chung-Lu model, such others. And these models are great in the fact that they have this small diameter, they have the power law, but the clustering effect is not so good. Then along came a few models that actually do get all three effects. For instance, hyperbolic random graphs, geometric and homogeneous random graphs. And of course, I'm not at all claiming this is a complete list. But here's the thing. These examples, at least the ones that we found while working through this, they all impose some geometry. There's some geometric object that's used to actually define how we make the probabilities between the various probabilities of certain edges. And so that's the big question that got us going here. Do we need this geometric assumption? Can we find a random graph model which has all three of these properties, but no underlying geometry? Okay. So let me go back to one of these models, which definitely won't do this, but it's a good place to start. So I'll start with the Chung-Lu model. So notation that I'll be using pretty much throughout the talk. For one, I will be thinking of everything asymptotically. This bold D up here, this will be a vector of length n, and will always be thought of as going to infinity. And I'll say that a Chung-Lu random graph, denoted by scripty g of d, is going to be a random graph where I add each edge uv independently with probability given by d sub u, d sub v, normalized so that all these numbers add up to 1. Important point, all the edges are independent of each other. Some nice things we know about this graph. Well, in expectation, we get its expected degrees are exactly equal to whatever the vector is that we put in. Great, so I get to pick my degree distribution. I can pick a power law if I like. I also know the diameter is quite small with high probability. Great. Clustering coefficient is way too small. That goes very quickly down to 0. So how are we going to fix this? Well, here's the model that we're going to introduce. So I'll start again with my vector d and a parameter gamma in 0, 1. And what we'll do is we will first draw a Chung-Lu random graph with this vector d. Great. I'll call that G naught. G naught will be used to denote the first stage of this construction for the remainder of the talk. Second step. Every time I have a path of length 2, flip a coin with bias gamma and add the edge if it comes up heads. Notice there can be a lot of paths between a pair of vertices. There can be many, many paths of length 2. If any one of them comes up heads, add the edge. We will refer to this as a random clustering graph denoted by C gamma of D. And of course, the question to ask, what are some of the properties of this new model? Before I get into that, any quick questions on the construction here?
Making your degree bigger.
Indeed, we will.
Are you going to renormalize in one way or another?
For the purposes of this, we won't. We will just let the degrees get bigger in this particular, as I'll talk about pretty soon. That said, there are some things that you could do to potentially mitigate that. Mm-hmm. The question asked was, aren't you making the degrees of the graph bigger? And the answer is very much yes. I'll have a theorem to that effect pretty soon. Okay, so before I get into the properties, let me introduce a little bit of notation. So volume sub k of d will denote the sum of the kth powers of the entries of my vector. and I'll just write volume of D for the first volume for simplicity. Hom HG will denote the number of times that a graph H appears as a subgraph of some other graph G. In particular, I'm assuming all my homomorphisms are injective and all my graphs are labeled. And with that in hand, I'll formally define the global clustering coefficient to be the ratio of triangles to paths of length 2. And finally, just for clarity, I'll say that a vector D follows a power law distribution if, long equation, what this means, number of entries in my vector with value x is proportional, or the log of that is proportional to alpha minus beta times the natural log of x. Beta here is going to be the important parameter. It'll be the exponent of the power law in the many definitions that we've seen already. Okay, so first off, our construction, C gamma D, contains a Chung-Lu model, so diameter can only get better. So won't spend too much time on that. Exactly as you were asking, let me give you this mild technical condition. I will talk about that in a second. Basically, the expected degree of a vertex is going to go up by a fixed factor relative to what it would be in my chosen vector. That specific factor, 1 plus gamma times volume 2 over volume of D, that is 1 plus gamma times the second order average degree of this vector. Nice scaling. The one small thing I'll notice up here, I do have this technical condition. Roughly speaking, what this means is that when I do this construction, I don't blow up and get any vertices of massive degree, by which I mean linear. Or another way to put it is this will actually sort of control the fact that my resulting graph is well formed, that my resulting vector actually gives me a degree sequence. So yes, the degrees do go up.
In this construction,
Mm-hmm.
you can't quite have infinite variance between the segments.
So you cannot with the tech. Yeah. With this technical condition, you definitely can't have that. In particular, if you work through the details, pick a vector that forms a power law. I can simulate power laws with exponents in this range, strictly greater than 2.5 and between 3. You can go much higher than 3 with this. That said, for the purposes of the results that I will be talking about, think of beta as being in this range. Big thing that's going to change here. Unlike the Chung-Lu model, edges are no longer independent of each other. They're now positively correlated. And that's basically going to be the obstacle that I will be dealing with for the remainder of this talk. And finally, well, talked about subgraph counts to begin with. We're going to have to address this problem. So I'm going to be thinking in the back of my head, I want to compute the clustering coefficient of this model. It means I need to estimate subgraph counts. So let's just think for a second. How would I construct a copy of a triangle inside this new model? Well, let's just think in the back of your head that I will denote with these dashed lines the edges that I want to add. I'll denote by red the edges that are already there, and I'll denote by green the edges that get added in the second stage of my construction. So let's just look at this edge, UV. Well, case 1, UV is already in my graph G0. I don't have to add it when I'm trying to build my triangle. That's great, but that's probably not going to happen. So let's look at case 2. Case 2, there's some vertex, which I'll denote by X, sitting way outside my desired copy of a triangle, but it's adjacent to both endpoints of my desired edge. This is great because I could potentially flip my coin for this path of length 2 and add in green the edge between U and V. This is also a fairly nice case. This is basically the proof of how the degrees change the proof for the expected degree of the new model. But there's a third case. This is the weird one. Here's the thing. I'm building a triangle. So what happens if I fill in 2 of the edges already? Well, that's a path of length 2, so I could flip the coin for it. I could get this third edge essentially for free. And this third case is really what's going to be causing all of the problems for embedding subgraphs in this new model. Because essentially what can happen is if I want to fill in this graph, there could be some additional edges in the copy of the graph that I'm trying to build that are actually going to help me to build the rest of this graph. I'm going to need to keep track of them. So what I'm building up to here we want to find some sort of subgraphs that, if they exist in our copy G0 from the Changlu model, if these graphs exist, we can use them to build a copy of our desired subgraph. I'm going to call these graphs extension configurations. Formally, what they'll be, it's going to, for an extension configuration for graph H, will be some other graph K, which contains the vertex set of H, and possibly with some other vertices that I will mark in red. It's going to have two properties. For every edge that's not already in my copy of H, so I added in a bunch of copies with K, but I might miss a few, there has to be at least one vertex in my extension configuration that's adjacent to both endpoints. And it's edge minimal. I can't, if I remove any edge from my extension configuration, I will not have this first property. Now, with a definition like this, pictures are worth 1,000 words, so let me give you a few. In fact, we're going to be looking at, again, extension configurations for the triangle. First one I've already shown to you. In fact, if I get two edges of my triangle, for free, I can get the third. That's one nice extension configuration, but that's all kind of internal to the triangle. So let's look outside. Let's say maybe I add a vertex sitting outside my triangle, but it's adjacent to all of my desired vertices. Well, if I have this copy of K13, complete bipartite graph on 3 vertices on one side and 1 on the other, well, this also forms an extension configuration. And then I can kind of get some stuff that goes in between the two. I can have one that's partly in and partly out, and one that's all out, but all of the vertices are outside. One, in fact, can prove that these 4 graphs are the only extension configurations for K3. A good exercise for you to think of, take C5, but instead of having this additional path of length 2 at the bottom here, just make that an edge going across. This is not an extension configuration. Yes, so take this C5, but make it C4. So get rid of this path of length 2 at the bottom, and just replace it with a red edge going right here. This is not an extension configuration. I originally thought it was when we were working on this project, which is why I bring it up here. Why? There are 2 different paths of length 2 that contain this edge. It's not an edge minimal extension configuration. You can find a smaller one, which in fact will turn out to be P2. I'm bringing this up now because in general, we have no idea what the set of extension configurations looks like for an arbitrary graph. This seems to be a quite tricky problem, one that I'm very interested in fact. Okay, so kind of the big informal theorem. There's some more technical assumptions which I've chosen not to state for the purposes of this talk, but the big theorem here is the subgraph count of an arbitrary graph in a random clustering graph is determined entirely by subgraph counts of extension configurations in the Changlu model. There's some really annoying constants that can pop up here. Basically, everything in this characterization is fully computable, but annoying to write down. Let me give you some more concrete corollaries of this theorem. So, if I give you a vector such that its third volume grows relatively slowly compared to its first volume, then the number of triangles is going to be determined by K13. And similarly, under the exact same assumptions, the number of paths of length 2 will be again determined by K13 with a slightly different constant out front. So the way to read these, this is the count of triangles in my new model. Here's some error terms. This is going to be a sort of constant that falls out from what you do to construct your graph from an extension configuration. And here's the count of the extension configuration itself. Yeah.
You can derive this for other extension configurations also?
Great question. The original theorem up here doesn't say something this strong. The original theorem says I can give you some linear combination of subgraph counts of these extension configurations that controls my subgraph count. However, under some mild assumptions, If you know what the set of extension configurations for a graph looks like, you can actually pick out the one that dominates all the others asymptotically. And that is precisely what's going on here. Is since I can write down all of them, I can compute expected subgraph counts for each one. K13 turns out to dominate everything.
Basically, that first statement is saying that the most likely way to get the edges in the triangle is by adding them in the last line.
Exactly. In fact, yeah, precisely. And you can kind of see the corollary that's about to come here. For one, exactly as you're saying, if I look at a single high degree vertex, that's where a bunch of my triangles are going to be coming from. Basically because they're all appearing in this second step, like you're saying. You can see the next corollary that I'm about to write down. Well, one, we can actually prove concentration for all of these subgraph counts. That's one of the corollaries of our general theorem. And second of all, here's the clustering coefficient. Simply the ratio of triangle counts to paths of length 2, which says with high probability, my clustering coefficient is exactly gamma. Or maybe another way to advertise this, pick your degree distribution, pick your clustering coefficient, we can build a graph that has them. So let me also finish off with a few other things that we can glean from this setting. And I will be focusing on a few more special cases for this. So let me focus and consider the case where we're looking at power law graphs with exponents between 2.5 and 3. Well, we can also do C4 counts. And I can enumerate the extension configurations for the force cycle. In particular, the force cycle count over here will be determined by K14, which for the exact same reason as it appears for the triangle, essentially I formed all 4 edges of C4 in my second step. Yeah.
Because we don't have cycles initially in the first graph, and all of these other extension configurations seem to have some sort of.
You're asking a great question. You're gonna see things get a little weirder in a second. Because you're right. All of the extension configurations that have shown to asymptotically dominate here up until now have been trees. And as you're saying, in most of these graphs that we're considering, there's just not that many cycles. Pretty much the only thing that you're going to be able to find is a tree. But remember, this works for any degree distribution. So I can pick a degree distribution that models the Erdős-Rényi random graph for relatively small values of p. If C is really small, I get the exact same behavior again, but if not, suddenly I get the 8 cycle. This is another extension configuration for the force cycle, basically replace every single edge by a path of length 2, and it turns out that's the one that dominates for a particular range. For particular values of C. The situation can actually get much worse. I've elected not to include worse examples here. If you consider graphs sort of like a version of Cheng-Lu where a bunch of your vertices have relatively small degree and then a bunch of them have big degree or vice versa, you can actually get even weirder extension configurations, which are like sort of cycles with added trees on the side. And for even bigger graphs, frankly, I don't know what it looks like. The point being, for small graphs, because we can enumerate all the extension configurations, we know what happens. So let me finish off with a few questions that I'd love to have answered. For one, basically we focused entirely on the clustering coefficient in this work. Most of these other properties are inherited from the Cheng-Lu model. What can we say about some of the other properties? Average distance, diameter, et cetera, et cetera, et cetera. Something I'd be very interested in. Second of all of our work was done purely theoretically. Everything that we have in our paper is just proofs. How well does this thing work in practice? In particular, I know there's a lot of interesting work that's been done on working with the Cheng-Lu model. I know many of you use it here. And finally, this is the question that I probably am most interested in for my own work. Which extension configuration shows up? So there are a few things that I can mention. Given any graph, there are two extension configurations that are sort of special. We've already seen them both. One is take the graph, add a vertex, add an edge to every single of the original vertex. I call this the cone, or as I denoted it here, K1 B of H. This is sort of like the minimal extension configuration if you don't allow any edges inside. There's also a maximal one. Take every edge, replace it with a path of length 2. This adds a huge number of new vertices, but for the right conditions, this is a maximizer. I think a pretty reasonable question here is characterizing which vectors give these two extension configurations as the dominant extension configuration. I think this is a reasonable question to answer. A much harder question, given a vector and a graph, which extension configuration maximizes, actually controls the subgraph count. That one, frankly, I think there's a lot of very tricky math involved in solving that one. And finally, how do we actually describe the set of extension configurations? The reason this might be hard, let's just only consider extension configurations which don't contain any edges on the graph itself. This is at least the number of clique covers of the graph, and probably much larger. If you only look at extension configurations that are contained within the graph itself, this is related to the set of what are called two-spanner trees, something that's studied in computer science, but they're not quite the same thing. And frankly, for mixed ones where there are edges partly in and partly out, I have no idea what's going on. So with that, thank you for your attention.